Swayam Prabha. Digital India. Educated India.
Today I am going to talk about smart materials. We have so far discussed about various types of materials where we have only focused on the mechanical properties of the materials. However, smart materials is one such group of materials where the mechanical property invariably gets coupled with other properties like electrical property, magnetic property, etc., and that actually generates some very beautiful, from the engineering point of view and also from the science point of view, some very beautiful effects in this particular group of materials. So let's look into that. So what we are first going to talk about is that what is a smart material after all, okay, and then we'll talk about the applications of the smart material, what motivates us that to work on the smart materials, and not only the materials, you can actually develop smart systems using smart materials. So we will talk a little bit about that. Then the smart actuators and direct and reverse effects in such smart materials. So let's unfold the story one by one. Now, the first important thing is that the smart materials are actually a part or a subgroup of a bigger group of materials which are broadly known as functional materials. So this we have to understand that what does it mean? Does it mean that not every material is functional, there are materials which are non-functional? It's not like that. All materials have some or the other functions. But when we say functional materials, what we mean here is that generally for engineering applications, let us say, generally from engineering applications point of view, from any material, what we expect mostly is a mechanical behavior. That means you have seen that from steel, from concrete, for iron, for aluminum, we always look for things like high stiffness, right, high modulus of elasticity or high yield strength. These are the things that we generally look for. But can there be a material which can give me a high stiffness along with something more? Let's say something like a changeable stiffness, that means a variable stiffness with some signal, say be it electric, be it magnetic. And similarly, the strength of the system can be increased, reinforced. And similarly, other behaviors like the dynamic properties or the deformation of the system. That means you can generate both positive and negative deformations in a system with the help of a non-mechanical way of doing, for example, with the help of electrical signals. So the materials which can respond to those type of other kind of behaviors also, these are the functional materials, and smart materials are a subgroup of this kind of functional materials. Now naturally this means that there is some energy transformation that is taking place in smart materials. So indeed the basic energy forms that gets interchanged are generally thermal energy, electric energy, magnetic energy, sound energy and mechanical energy. Basically it is transformation between mechanical energy and all these energies. One important thing of smart materials is that they are very much analogous to biological materials or so-called living systems, right? So they are many times actually living cells. They are many times actually kind of an analogy people draw between them and the living systems. Why? Because they are adaptive. You can, I told you just now that the stiffness you can change. So similarly you can change their shape etc. in some materials. So they are adaptive. They are cellular in function. What does it mean by cellularity in function? It means that even if you break this a kind of a smart system into 2 parts, 3 parts, okay, if you break a clock into 3 parts, the clock, none of the parts would work. But if you take a smart material and break it into say 3 parts, each part, even though its performance may degrade a little bit, but each part would be fully working. So that's the cellularity that is present in such materials. They are self-sensing and actuation, so which means that you can actually generate forces from them. Also, you can use them as a sensor. So that is why they are self-sensing and actuation. And not only that, you can actually control them. You can change these behaviors. Finally, these sensors and actuators are highly embeddable. Okay, we have talked about composites. In that context, this point is important because the composite is developed in a laminar manner. So there are several lamina, suppose in a composite beam. Suppose we are looking at the composite beam like this, you can very nicely embed one smart sensor inside, which will give us all the information related to the stress, related to the strain, temperature, cracks propagating, and so on and so forth. So these are some of the advantages of the smart materials. Now, smartness, how do we define? If you look into a dictionary, then you would see that something which is not smart at all, the worst sense is something which is stupid. Then maybe dumb, foolish, trivial, and then as the intelligence increases, you will start to get terms like sensible, smart, clever, intelligent, wise, etc. So, where are we in these smart materials systems in terms of the intelligence? Now, currently we are somewhere in the domain of highly sensible. So, here till smart, clever, or maybe just reaching the poorly intelligent level. That means still we are not able to replace a living system completely by an artificial system. That is something still something like a science fiction for us, but we can go very close to that with today's advanced materials. Now, there are actually 2 types of smartness. One is passive smartness and another is active smartness. Passive smartness, I can give you an example. It's like the rocket nozzle of a space shuttle. If you look at it, you would see that it consists of several layers. For example, it has a layer of silver coating, then it has graphite, it has silver coating, graphite, ceramic layer, and steel. Each layer is intelligently kept in order to do certain things. For example, silver coating, what does it do? It actually spreads the temperature over the graphite layer very uniformly, and that actually kind of helps to avoid any thermal stress concentration. Then there is ceramic layer. Similarly, it also works in a slightly lesser temperature range. And then there is steel. So as and below the steel you have basically the system itself inside. Okay, so as you are going through the space or re-entering mostly into the earth, you are getting high temperature due to the friction with the environment, and that temperature should not affect the environment inside. Every system should remain functional inside. That is the kind of the driving force because of which you actually develop this kind of a multi-layered system. But one point, this system is in open loop. Tomorrow, if because of some reason the temperature changes or some other factor comes into picture, corrosiveness, let's say we are entering not Earth but some other planet, this system would not work. So that is the problem of passive smartness. That is, it is usually an one-time design. It lacks also the inherent capacity to transduce the energy, and sometimes it can at best work as sensors, the passive systems, but not as actuators. So active systems on the other hand can actually change themselves. Now, if you look at active smartnesses, then the features that you will see is that they can modify their geometric or material properties. Thus, they have a inherent capacity to transduce the energy, and they can act both as sensors and actuators. Of course, there are some very specific materials which are like optical fiber, which are generally not used as actuators, only as sensors. Now, the four very important materials which are used in the group of smart materials almost in regular basis are piezoelectric material, shape memory alloy, electrorheological fluid, and magnetostrictive material. For piezoelectric material, if I apply stress, I will see a change, in terms of the electric field. It was, like you can do a small test. So, for example, you take a good size sugar crystal, and in a completely dark room, you hit it with a hammer. You are definitely going to see a streak of light coming out, and that is actually the electric discharge that is happening in the system. So that is, a kind of a telltale sign of a piezoelectric material. So sugar crystal, Rossel salts, these are some of the naturally available piezoelectric material which will show this piezoelectric effect. And this effect that the stress is producing an electric field discharge is also, I will talk about it later on, but this is also known as the direct effect of piezoelectricity. But there exists another effect which is known as the indirect effect. That means instead of applying mechanical force and getting some change of electrical field, what if you apply electrical field to piezoelectric material? You are going to see a change in the mechanical strain. That means it's going to deform, it's going to change its shape, and that is the indirect effect. Okay, so or sometimes people also call it as the reverse effect or the converse effect. There are very similar names of it. Now that's about the piezoelectric material. Then you have materials like shape memory alloy, which is basically one of the very popular material is nickel titanium alloys, and here if you apply temperature, you are going to see a huge change in terms of the deformation. Not only that, in many cases, if you actually reduce the temperature, you are going to get back to the original memorized shape. So there are actually two types of these effects I will later on discuss. One is called two-way shape memory, another is called one-way shape memory. So in two-way, it actually memorizes both the high temperature as well as the low temperature shape, but in one way it memorizes only one, that is the high temperature, the shape, original shape at high temperature. Then these two of course respond to the electric field or the thermal field in terms of changing mechanical strain. But there are some materials like electrorheological fluid where if you apply the electric field, you will see there is a change in viscosity. Once again, in a laboratory, you can try this kind of very simple test that you can take a colloidal suspension of starch, or suppose something like this maida kind of a thing. Okay, so wheat powder, so that you actually disperse it in a slightly acidic medium, and then you apply high voltage. What you will see is that colloidal solution will start to get, so if you apply high voltage in two electrodes, you will see that there is a bridging effect happening, okay, close to this. So all the particles will start to flock around this, and there is a bridging effect. So that means the viscosity is going to get changed around these electrodes. So this is electric field which is responsible for change in viscosity. There are many fantastic applications, particularly not with electric field but with magnetic field, and we call such materials to be magnetorheological material. Very similar to this effect, but the source responsible is not electric field but magnetic field, so magnetorheological field. Now the magnetic field can also be used to generate mechanical strain, and that happens for a group of material like terphenol D, terbium, iron, and some amount of dysprosium can actually bring this change. So there are a whole lot of smart materials which manifest these types of very interesting changes. So if we compare between a traditional versus smart system, traditional systems are designed for certain performance requirements, for example for certain load, certain speed, certain lifespan. They are unable to modify its specifications if there is a change of environment. Whereas for smart system, we want to re-emphasize that they can accommodate unpredictable environments. They can meet exacting performance requirement, and they offer more efficient solutions for a wide range of applications. Now, if I actually look at the smart materials which possess this ability to change their physical properties in a specific manner in response to specific stimulus input, then commonly used materials are the piezoelectric material, as you can see here in this little animation, that you are changing the electric field which is generating the charges, and in response to that, this whole thing realigns itself, and as a result you are getting a mechanical deformation in the system. Similar thing you will notice in the magnetostrictive material with the change of magnetic field. In fact, first it was noticed in ferromagnetic material like iron. Okay, so Joule first noted that a change in the shape of a magnet is happening with the change of the magnetic field, and that's the magnetostrictive. For phase transition dependent materials like shape memory alloy wares, what happens is that you use a temperature which is high enough. What will happen is it will go from martensite to austenite phase. You can do all sorts of deformations, okay, but if it is a one way, for example, you can deform it in the martensite phase itself, and then if you increase the temperature, it will exactly go back to its original shape. And if it is a two-way one, then this happens between both low and the high temperature. So that is two-way shape memory effect. Electromagnetorheological materials, I already told you that they change in viscosity in response to electric or magnetic field. For example, the magnetorheological materials, one of the best example is iron nanoparticles in a solution like silicone oil. So silicone oil and silicone oil plus iron nanoparticle suspension, and then you apply magnetic field, you will see a similar bridging effect, and that completely dramatically changes the viscosity of the solution. So why smart sensors and actuators are important today? The first important thing is that the response, the real time response, it is very fast. So it is very fast working. Okay, in today's world, for example, you think of your single lens reflector SLR camera, you want a quick change of focus, and who does that? A piezoelectric crystal. So a real fast response you get. It exploits the functional properties. That means a material both works as a mechanical load carrying system as well as it does functional work. So that means it makes the system very compact, and it has better embeddability with the composites. I told you already that with the advent of composites, smart materials application increase like anything. It has minimum effect on structural properties. Some of the smart materials are quite good in terms of their structural properties. Reduction in weight, of course, less power consumption, and better reliability. So these are all the driving factors why smart materials are increasingly being used for developing sensors and actuators. There are a range of applications of them. I have only shown a few of them here. For example, this one in the left side, as you can see, that this is a platform. Okay, so this is also known as a Stuart platform. So it has actually, various legs in it. The idea is that if there is an excitation force at the base of the system, there is an excitation force happening, and you are not going to allow this excitation force to pass through this system and excite a little very highly precise machine that is sitting on top of it. You want to stop that. How do you stop it? Well, one way to stop it is that suppose it is getting excited at a particular frequency level. Okay, so with respect to time, suppose there is a particular amplitude of this system. Now you want to design these legs in such a manner that it is completely detuned from this frequency. That means it's not going to resonate. If it does not resonate, then it is generally going to absorb this vibration within itself. So how do I do it? Because this base excitation can keep on varying. One way to do it is you use piezoelectric material which can change its size. Okay, so you can increase or decrease the leg as and when required, and through that you can stop the excitation to pass through. There is another very interesting application of smart materials, that is in the shoes, for example, that if you keep such smart materials below the sole, you can actually get energy transferred from mechanical to electrical energy here. So as you are walking, your mechanical energy is getting generated, and you can transform it to electrical energy, and you can store this electrical energy, and as a result you can use it for charging low power electronic devices. So that is something like this is coming up in a big way, low power electronic devices. There are many other applications. For example, this one is not very clear to this, like a butterfly wing, and this is a if you apply temperature, you are going to see that this wing is going to flap. So you can generate a kind of a insect flapping with the help of this kind of system. And here is another system where this is a master slave. So this is a master finger. The idea is that whatever the master finger is doing, okay, the smart sensors here are actually mapping that, and then this is the slave finger. So the slave finger is going to copy it. So this you can use for in future for things like applications like telesurgery. Okay, so the master finger far away can do something, and the slave finger can actually copy that movement. Now then, if I actually summarize all these smart materials from the sensing and actuation point of view, we will get this beautiful matrix. On this matrix, if you look at these columns as outputs, current, charge, magnetization, strain, temperature, light. If you look at the input, electric field, magnetic field, stress, heat and light. So if I consider a diagonal element in this matrix, that is stress versus strain, then what comes in the diagonal element is the elastic modulus. So that is not a smartness, because every material deforms under stress. Then what is smartness? Smartness is if I can generate strain not with the help of stress, let us say with the help of an electric field. So you come here and you are generating strain, that is what is known as reverse piezoelectricity, that is smartness. Or with the help of magnetic field you want to generate, then this is Joule effect magnetostriction, that is smartness. With heat, shape memory applications, that is smartness. With light, photostriction, that is smartness. So essentially this whole column here, except this diagonal term, they are actually actuators. Okay, so where these off diagonal properties of the material are used for building up the actuation. On the other hand, if I look at these properties where the strain is generating current or charge, or it is generating change in magnetization, change in temperature, or change in light, then these regions are actually used as sensors. So the horizontal block is for smart sensing and the vertical block, except the diagonal, is for smart actuation. So there are two types of this smart sensing and actuation. One is what? You are applying stress, that is the mechanical load, and you are getting a change in electric potential, okay, or magnetic potential, or so on and so forth. Then this is called direct effect. I mean, there is no reason for it, but this was one of the first things that was actually observed, that by Curie's, that once you take a small crystal, you apply a stress, you are going to get charges develop. That's the direct effect. If you apply an electric field, in fact that was initially a theoretical proposition by Lippmann, and then later on it was verified by people, that if you apply the electric field, you are going to get strain generated in the sample, and that is known as the reverse effect. So naturally the direct effect is generally used as sensor, and the reverse effect is generally used as actuators. So this is the two very important effects we have to keep in our mind as far as the smart materials for sensing and actuation comes into picture. We are talking about the direct effect, and this direct effect is available in piezoelectric materials, and also the direct effect is available in a material which is a polymer, and this polymer is actually known as PVDF, polyvinyl difluoride. Now it is also available in magnetostrictive materials and in optical fibers. Remember that the direct effect means you are applying stress and you are finding a change in electric potential or in magnetization. Now converse effect, on the other hand, are found in ferroelectric perovskites, piezoceramics, PVDF. They all respond to electric field by the change in shape. Similarly, tarphenol D, amorphous made glasses, they show a similar effect with the change in magnetic field, and shape memory alloy respond in a similar manner but with a change in thermal field. And electromagneto-rheological fluids, they respond to electric magnetic field by changing its viscosity. So this is a whole group of materials which responds to electric, magnetic or thermal stimulus, and there is either a change in strain or a change in viscosity, and that is what is our converse or the reverse effect, which is used to build the actuators. Now if I compare these traditional versus new actuators, that is the smart materials like piezoelectric, magnetostrictive or ultrasonic motors, you would see first thing interesting is that their displacements are quite small, but their accuracy is very high, and also their response time is very low. That is why I told you that they are very fast. In comparison to all the traditional materials, they are actually much better off. So you can do a real time control of a system using this material. Now in the smart actuators, there are a whole lot of actuators like electric field, those which exploits. There is piezoelectric and electrostrictive actuators. Then you have electrostatic actuators which are MEMS based, and you have electrorheological fluids. In the magnetic field category, you have magnetostrictive actuators and magnetorheological fluids. In the chemical, there are some coming up in mechanochemicals, we call them. And in the heat, there is shape memory alloy and shape memory polymer. And in the light, there is this photostrictive materials. So there is a whole group of smart actuators that are available today. Just for comparison, properties of a few smart materials. One important property is the free strain. That means how much of deformation happens if it is not loaded. Piezoelectric material, you get something like 1000 parts per million, and which can go as high as 20,000 for shape memory alloys like nitinol. Elastic modulus, on the other hand, is about 62 gigapascal, that is for the piezoelectric material, and for the shape memory material it varies between 27 to 89. PVDF is the lowest one, it is very soft. Terphenol D somewhere in the middle. Band is another interesting thing, that means how fast the material can react. Piezoelectrics 0.1 Hz to 1 gigahertz, same for PVDF, little less for terphenol D, which means they are all very fast, but this 20,000 one, they are not that fast, they are very slow. That is the only one material, smart material, whose response time is quite slow, but the actuation strain is very high. So this is where we will end, and in the next lecture we will talk about this material like piezoelectric material, their constitutive equation, polymers and composites in much more details. Thank you.